In the last video, we got 3 important documents from the registration assistant: the full protocol, registration guidelines, and search strategy. In the search strategy document, it already gave us search strings for every database: Scopus, Web of Science, PubMed, all of them. The AI drafted these for us. But there's one problem that many people discover after they go straight to searching. The search string hasn't been tested. We don't know yet whether it's too broad, too narrow, or has syntax errors that the database won't accept. Imagine we paste that search string into Scopus, hit search, and get 266,000 records. How do you screen 266,000? It's not feasible. In the past, to fix this, we had to manually run and check one by one. Remove a term, add a filter, test again, and repeat. It could take days just to fine-tune a single search string. The search string optimizer is what helps us with this. We give it the problematic search string, we tell it what the problem is, and the system generates a prompt that asks the AI to diagnose, fix, and give us options. Not one option, 3 options with different levels of aggressiveness. sr.online is our search string optimizer. Simple. There are 3 steps to follow: input, optimize, translate. Step 1, we enter our information. Step 2, the AI optimizes our search string. Step 3, after optimizing for one database, we translate to all other databases. One complete workflow. Before we start, we need 2 important documents to run this web app. Both of these we already got in the previous video. You can see here in our project folder, we now have 3 documents marking our progress. But in this video, we'll use the full protocol and the search strategy document. From the search strategy, we'll take the search string. From the full protocol, we'll take the PICO and eligibility criteria details to give context to the AI. This is our search strategy document. You can see the databases to search: Scopus, Web of Science, PubMed. Search parameters are already there. English only, no date restrictions. And here's the search string the AI drafted for Scopus. It's long. It already has the Scopus-specific syntax style. We copy the search string first, then we test it in a Scopus database and see what we get. Open Scopus. You can usually access it through your university portal. Now go to Advanced Document Search. Paste the search string. You can see all the operators: title, ABS key, and limit to. Click Search. $266,866 documents. We're not doing a systematic review, not opening a library. 266,000 records is not feasible to screen. Even the first result has nothing to do with our topic. The search string we're using right now is far too broad. So now we need the search string optimizer to fix this. Go back to srstring.online. Open it side by side in split view. On the left, the search strategy document. On the right, the optimizer tool.
The system has generated a prompt based on the details we filled in. Click Copy. Open your AI chatbot and start a new chat. Select Thinking Noddle. Paste the prompt, then run. It will analyze our search string, compare it against benchmarks from published systematic reviews on the web, diagnose our problem, and propose 3 versions of an optimized search string. Watch the step-by-step process. Step 1. Syntax check. It found 1 syntax error, a spacing issue on limit 2. Small, but it can affect results. Step 2. Benchmark. This is the powerful part. The AI actually searches the web to find systematic reviews similar to our topic and checks how many results they got. Some got around 1,000, others got only 260. So our 266,000 is clearly far too high. Step 3. Diagnose. 4 problems, all high impact. First, there are acronyms in our search string that are high noise in Scopus. The same abbreviations are used by other fields pulling in unrelated results. Second, there are proximity terms that are too generic. They capture literature from other fields unrelated to our topic. Third, the intervention block is too broad. Some terms are too general without specific context for our topic, capturing everything. Fourth, there are no study design constraints, so observational studies and irrelevant literature get included too. The AI doesn't just say your search string is too broad, it tells you exactly why it's broad. This is diagnosis, not just observation.
Step 4. Tree-optimized search string options come out. Option A. Conservative, 97% reduction. It removes noisy terms, adds more specific context, but keeps the broad intervention terms. Wide capture, low risk of missing eligible studies. Option B. Moderate, 99.5% reduction. It adds study design terms, excludes reviews and case reports, limits to articles only. Option C. Aggressive, 99.8% reduction. It requires the main terms of our topic to appear in the title, not just the abstract. Very strict. 3 levels. Pick based on your needs. We test each one, starting with option A, conservative. Copy that search string. Go to Scopus, Advanced Search, paste option A, click Search. $942 documents, from 266,000 down to 942, under 1,000, hitting our target, and the first result is already relevant to our topic. Option B, moderate. $114 documents, much smaller. Results are more focused. Option C, aggressive. 25 documents only, very tight, but there's a risk of missing eligible studies. And notice step 5, trade-offs. The AI explains for each option what it preserves and what the risks are. Option A keeps high sensitivity but might still exceed 1,000. Option B is more aligned with the study design in our protocol, but might miss studies that don't state design terms in their abstract. Option C is the strictest, but has higher false negatives. All transparent. We make decisions based on data, not guesswork. For our example, option A fits well, 942, reasonable for screening, so we go with option A.
Now we have an optimized search string for Scopus, but a systematic review can't search just one database. In our full protocol, we specified 4 databases: Scopus, Web of Science, PubMed, APA PsycINFO, Google Scholar. Every database has its own syntax. If we get the syntax wrong, the database rejects it or gives incorrect results. In the past, we had to manually rewrite the search string for each database, or use Polyglot from TerraTools. But Polyglot assumes your search string is already optimal. Our tool does both. It optimizes first, then translates in one workflow. Now, paste the optimized search string we chose, option A, source database, Scopus. Select which databases to translate to. Follow what our full protocol outlines. PubMed, tick. Web of Science, tick. PsycINFO on OBD and EBSCOhost, tick. Google Scholar, tick. Scopus is grayed out because that's our source database. Generate translation prompt. The system produces a prompt with all the context: source database, optimized string, target databases. Notice the instruction: paste into the same AI chatbot where you optimize your search string. The same chat, not a new chat, because the AI already has context from the optimization. If you open a new chat, all that context is lost. Go back to the same AI chatbot, paste the translation prompt, run.
Now we verify each database. PubMed first. Copy the PubMed string from the translation table. Paste it into the Advanced Search Builder. Click Search. $552 results in PubMed, and the first result is relevant to our topic. On track. Web of Science. Copy the translated string, paste it into the query builder. $808 in Web of Science. Relevant result count. Google Scholar, 147. All databases verified. Search strings are all working, results are all reasonable, and most importantly, the results are relevant to our topic.
Let's recap what we achieved in this video. We started with a search string that returned 266,000 records. Far too broad, not feasible. The system diagnosed 4 specific problems. It gave us 3 optimization options. We tested each one in Scopus. Conservative got 942, moderate 114, aggressive 25. We chose conservative. Then in one more step, we translated the optimized string to PubMed, Web of Science, Google Scholar, and PsycINFO. All verified, all copy ready. One critical thing after this: update your documents. The search strategy document updated with the new optimized strings. Remove the originals, replace with the optimized versions. And a full protocol too. If there are changes to the database list, update it. These documents follow us all the way to the end, so do it properly. Next, we're ready for searching. We'll go into each database, run these optimized search strings, download results in RIS format, and prepare for the deduplication process. But the search strings are already optimized, so we know what we'll get is reasonable. Thank you for watching. See you in the next video.